This talk is by Nicholas Mosier, and it is doing return-oriented programming with a second stack, so that should be exciting. Before we get started, I have a couple announcements. We'd like to say thank you to our sponsors, especially our Inner Circle sponsors, Critical Stack and ValMail, and also our stellar sponsors, the National Security Agency, BlackBerry, Cylance, and Microsoft. So another announcement, these talks are being streamed to YouTube, so if you have any questions, please raise your hand, and I will bring the microphone over so everyone can hear you. Be sure to silence your cell phones out of courtesy for everyone here, and let's get started. Thank you.
Hi, everyone. Thanks for coming. So in this talk, I'm going to present a ROP compiler that accepts a Turing-complete source language. And so as the first title suggests, what's most special about this compiler is that the shellcode program has access to a second stack. From now on, I'll just call that the Shellcode Stack. And then in this talk, I'll also demonstrate what you can do once you have a shellcode stack. And so it turns out one of the things you can do is you can write an exploit that recursively computes the Fibonacci sequence. So in the end, I'll present a demo of this. And so I'm Nicholas Mosier again, and Pete Johnson was my mentor in the process of working on this project. And I go to Middlebury College. So first, just a brief overview of the presentation. So again, the central feature of this compiler is the shellcode stack. That's what all the other features are sort of based around. And so my main goals in this project were, so first of all, to show that it's possible to create a shellcode stack using ROP gadgets. And so this shellcode stack, the idea is that it would be used to maintain, to record the shellcode's program, or its call stack, and the state of each function, the local variables, et cetera. And then again, so the second goal is just to see how many usual programming features you can recreate using if you have access to a stack. So the source language I call ROPC-IR. That supports shellcode subroutine calls and calls into library functions in libc. And so I did do all my work on a virtual machine running x86 64 Arch Linux. And so a brief outline of the presentation is, first, I'll give a very brief review of ROP and how gadgets work. And then I'll briefly discuss previous ROP compilers. And then I'll introduce my compiler, inventively called ROPC, and also the source language that it accepts, ROPC-IR. And then I'll go into detail about how instructions in ROPC-IR work, how you write a program, and I'll conclude with a couple demos at the end. So let's start. And so briefly, a brief refresher of x86. I know this is going to be a review for most people, but just the most important features for the purpose of this talk are that, so it's a complex instruction set. The most important registers are the stack pointer, RSP, RBP is the frame pointer, and RIP is the program counter, the instruction pointer. And then some general purpose registers are RAX through RDX, et cetera. And also throughout the talk, I'll be using Intel syntax. So that means the right-hand side is the source and the left-hand side is the destination. And so now just to clarify some terms I'll be using. So by target program, I just mean it's a program that has a vulnerability that we're trying to exploit using ROP techniques. And the target stack is the stack that program uses. It's the stack everyone is familiar with. And so the shellcode, of course, is just the sequence of bytes that this compiler produces in this case. And the shellcode stack that's the only new concept here. However, it's not that much different from the target stack. So it's the same to the shellcode as the target stack is to the target program. So again, the shellcode stack is used for recording the execution state of the shellcode. So now a brief review of return-oriented programming. So basically, it's a type of attack that works if there's a non-executable stack. And so gadgets are the foundational units of ROP. There's short instruction sequences that end in normally RET, and you find them in executable memory. And so while gadgets can be found in any executable memory, normally they're just in libraries such as libc, since every C program will map those. And then if you chain those together, you can perform arbitrary computation given you find a Turing-complete set of gadgets. And so a ROP exploit works just by overflowing the target stack and causing the target program to return into these gadgets in succession. And of course, it's called return-oriented because each gadget ends in a return instruction. And so now just to show some gadgets that I found in libc that I was, these came in use when I was implementing things later on. So here's a conditional move and a move RSP RDX, two instructions. And this is just to emphasize that there are a lot of gadgets in libc, so you have a lot to work with. So now I'll just discuss some previous work done on ROP compilers. So very early on in the 2000s, it was well known that you could come up with a Turing-complete set of ROP gadgets. However, it's not very clear how you would chain those together to do exactly what you want if it's more of a complex shellcode. So that's where compilers come in handy, is they allow you to write a program in a higher level language and compile that down to shellcode, which is just a series of gadgets. So Q is one of the earlier compilers I found, so it's in 2011. The source language called Cool with a K, it is compiled to shellcode, but it's not a Turing-complete language. So later on, there was microgadgets in 2012. So it was Turing-complete, but it sometimes was destructive to shellcode on the target stack when making library calls. And it didn't support subroutine calls. So I think one of the closest compilers to the one I'm presenting is Pact's ROP compiler in 2013. That actually did have a shellcode stack as well. It was Turing-complete. However, its support of library calls, when it would make a library call, sometimes it would cause the shellcode to crash because it would overwrite the code on the target stack. And then finally, there's Jeff Ball's 55 Pi ROP. So that is actually based on Cool. It does have support for 64-bit systems, but it has the same flaw in that it's not really flaw, but it has the same limitation that it's not Turing-complete. Okay, and this is just a brief diagram of what I just said. Pretty much, some of these compilers support, so every single feature is supported by some compiler, but there isn't really a compiler that supports all those. So I'm just going to present how mine fulfills all of these. So finally, I get to how my compiler works. So it works on x86-64 systems. So its main features are Turing-complete and has a shellcode stack, and then all the other features come out of these two things. So I'll give a brief overview of how compilation works. So as input, the compiler takes in source code, which is written in the source language called ROPC-IR. It's really more like a made-up assembly-like language, hence the IR, intermediate representation. It also takes in translation rules and gadgets assignments. This tells the compiler how to implement each basic operation in gadgets found on a specific system or version of libc. And then finally, there are configuration parameters. They're target-specific, such as where libc is mapped for this target. So this requires that ASLR not be enabled because the compiler has to know where libc is for the particular target at compile time. So and then as output, so the source program's fed into the compiler, and then as output, it just produces shellcode that can be fed directly to the vulnerable program, the target program. So again, the main features are it's Turing-complete, it uses a shellcode stack, but also through this shellcode stack, it's able to support subroutine calls into shellcode, other shellcode routines, library calls into libc, and also system calls. And also, it does run on 64-bit system because most previous ones were for 32-bit architectures. So now I'll go into, since the shellcode stack is like the core feature of ROPC, I'll go more into depth about that. So unsurprisingly, designing the shellcode stack was a bit of a challenge. So I'll just walk through how I approached the problem. So of course, since we have a shellcode stack, we're going to need to have a stack pointer as well. Let's just call it SP, the shellcode stack pointer. We don't want to hard code the pointer unless we absolutely have to. But that means it must be stored in a register. But the problem is that if we also want to support library calls, those can destroy registers. So how are we going to preserve the shellcode stack pointer if it's stored in a register? So that's the problem. The solution I came up with is we could just repurpose the target frame pointer, RBP, as the shellcode stack pointer. Since RSP is already being used for the target stack, we can just use RBP for the shellcode stack. And this is just because, as part of the C calling convention, all C functions preserve RBP. They start with a push RBP and end with a pop RBP. That's how we know that. So from now on, just consider SP, the shellcode stack pointer, to be an abstraction of RBP. So, and then now we know where we're going to keep the shellcode stack pointer, but what would we actually use as a shellcode stack? Well, this is an easier problem. You can just make a call to malloc. And there are two advantages of that. We get a dynamic address. It's not hard-coded at all, and it's arbitrarily sized. And so one of the advantages that this has over previous approaches is it's not, for example, one previous compiler used the data section of the target program to emulate the stack, the shellcode stack, but that has limitations. That's only a limited size, and the shellcode pointer, stack pointer, was also stored at a fixed address in memory. Okay, so now that I've gone over basics of how the compiler is going to work, I'll discuss the source language, ROPC-IR. So again, it's assembly-like. So a program written in ROPC-IR just consists of ROPC-IR instructions, just like any other assembly program. And the ROPC-IR instruction space is the target stack. So because that's just by nature of how return-oriented programming works, you overflow the target stack with gadgets that you want to return into. So that means ROPC-IR instructions, when they're compiled, they will exist on the target stack at runtime. So because of this, the register RSP really becomes the shellcode program counter. So we can just abstract that as PC. So we'll call it PC. That's the shellcode program counter. And so also it's useful to think of ROPC-IR instructions as interfaces. So really, ROPC-IR is like an instruction set architecture. The instructions needn't be implemented. They're not defined by how they're implemented in gadgets. They define the inputs and outputs, and then for whichever system you want to compile shellcode on, you just have to find gadgets for that specific system that will implement that all the instructions. And so that separating the instructions from their implementation makes it more portable. So I'll just go over the architecture of ROPC-IR. So it's 64-bit, it works on 64-bit values and has 64-bit word size. And it has 3 registers. So the accumulator is ACC. So under the hood, that's really used as RAX, but we're abstracting that away just as the accumulator. And so the shellcode stack pointer is SP, and that's really the x86 RBP register. And then the shellcode program counter, which is called PC, under the hood, that's really the RSP register. And so these are all just abstractions of existing registers in the x86-64 architecture. And then there are 2 flags, so the 0 flag and the carry flag, and that's just used for conditional branching, which makes it Turing complete. Okay, and so this is here we have a table of all ROPC-IR instructions. So the first row, those aren't really instructions. Those are assembler directives, basically. The last 4, you'd probably see equivalents in other assemblers, like DQ just places the literal 8-byte value in the shellcode. The only new one is the ret directive that tells the compiler that the next 8-byte value is really an offset from libc, and the compiler should compute where that's going to be at runtime, and because it's intended to be used as a gadget to be returned into. And so now to the actual instruction. So there's a move instruction that's pretty basic, self-explanatory. More importantly, there's the stack operations. It has pretty usual stack operations, so push, pop, allocates space on the stack, and so on. So and memory is, there's the load and store instruction. Each of those just work on arbitrary 8-byte addresses. There are arithmetic instructions, still pretty basic. Comparison. So comparison is important, so we can set the 2 flags that the ROPC-IR has, and we can use that flag to perform conditional branching. And so that's very important for being Turing complete. So if we look at the branching instructions, there's one just direct jump, but then the remaining ones are all conditional branches. And finally, there's the call instructions. So the call instruction, that just calls a shellcode subroutine. So that's just another routine in the shellcode program that it'll call, and then that subroutine returns with the ret, of course. And then also there's the LIBCALL instruction. That's probably the most complex instruction. That will make a library call. So it'll call a library function in libc, and it's important to know that it's a safe library call. It doesn't run the risk of destroying the shellcode program that's on the target stack, because it's effectively sandboxed, as I'll go into detail later. So now I'll just go into show how these instructions are actually implemented. So this is the most basic, just the move instruction. So it's very simple. It just takes one gadget and then one value. And of course, what this does is it moves a value into the accumulator. So this one gadget that it uses is just a pop RAX. So that works by when the shellcode returns into that gadget, it'll pop the next value in the shellcode into RAX, which happens to be the value we want to move in. So that achieves the desired effect. Then it goes on to the next instructions in the shellcode. So here's the negate instruction, but you can soon see this is more complex, but you begin to notice that these gadgets here, they're not very informative. Just listing the addresses is not very informative at all, so that's why my ROP compiler allows you to rename them based on what they actually do. So this is how it's actually written. And then these sort of wrappers are associated with the actual gadget somewhere else. And so from now on, I'll call these ROPC-IR micro-ops, the things that are prefixed with an underscore. That's because you can chain them together to build an actual instruction, but they're not just gadgets because they actually have names. Okay, so here's the push instruction. This is where it starts getting a bit more interesting. This is where we're actually implementing the shellcode stack, basically. Still, it's not too complex, really. All we're doing is preserving the accumulator. Then we move the shellcode stack pointer into RAX, do some math on it, so we subtract 8 from it, so decrement it, and then just store a value in that at that spot, and then restore the value of the accumulator, and then we're done. So that's all there is to it. And so, okay, now the jump instruction. This is also quite simple. It only takes one gadget, and that's all. But I just wanted to mention this because it could be a bit confusing, because you're moving a value into RSP, but the real effect that has is causing a jump in the shellcode to a new value, putting a new value in the shellcode program counter. And that's because PC, the shellcode program counter, is just an abstraction of RSP. Okay, so now we'll do a conditional jump. So this, the only trick here is just in the cmove E instruction. So that is basically conditionally moving a new address into a register, and then we just load that register into the program counter. That's all there is to it. And OK, so finally the call instruction. So this is where this gets more interesting, because now we're actually starting to use the shellcode stack. So previously we weren't really using the shellcode stack except for the push instruction, but now we actually get to leverage it. So it turns out, so first I'll explain how the call instruction works. The arguments are pushed onto the stack before the call instruction is executed, and then the shellcode will execute this call instruction. So since we've already implemented the push instruction, most of our work is done, because all a call instruction really is pushing the return value onto the stack and then jumping to the subroutine address. So that's all there is here. And so the only weird thing is the $sign plus 240. So that's the current program counter plus 240. That happens to be the size of what the entire call instruction compiles to. So which will be the return address. And I just want to mention this does demonstrate the power of the shellcode stack, because now implementing a subroutine call is just a trivial thing to do. Only requires 2 lines. OK, so now we get to library calls. These are significantly more complex than anything we've seen before, that I've introduced before. Our previous approach that we took for subroutine calls won't work. So the problem with library functions is that they break the abstraction of the shellcode program counter, because they think that RSP is a stack pointer, not the shellcode program counter. And they're going to use it as the stack pointer and write values onto it and potentially corrupt the shellcode. So that's a big problem. And we can't let that happen. So we somehow need to figure out a way to sandbox the library call stack frame. But so we've already designed the shellcode stack, so why don't we use it? We can just point RSP to the shellcode stack pointer, SP, and then execute the library call, and then it's going to use the actual stack as a stack for itself. So that would be exactly what we want, but there is another problem. If we point RSP to the shellcode stack pointer, we're somehow going to we need to figure out a way to resume execution after the library call finishes. This isn't as simple as it may seem, because library calls don't think of, they have a different notion of what a return address is. That they think a return address is a return address into x86 instructions, while our return addresses in ROPC are return addresses into shellcode instructions, which really compile down to just a series of gadgets. So the trick to this is just putting an extra pop RSP gadget on the shellcode stack. And so that will sort of restore that abstraction. So the library call will turn into pop RSP, which will then restore the shellcode return address. It'll do exactly what we want. So since the library call is so complex, I'm going to just do a walkthrough of how it works, with actually 2. So one's a simplified version, and one's a mostly fully complex version. So we'll start at the simplified version, of course. So what we want to do in this walkthrough, we're going to be trying to call printf, basically make a library call to printf, which is very useful when you're writing programs to print something. So just to orient you first, on the right-hand side, we have the shellcode instructions. These are actually located on the target stack, but let's just think of them as the shellcode instruction space where PC is pointing. And then on the top left is the shellcode stack. So that's a completely different address space, or memory space. And then the bottom left is the libc instruction, so there's executable memory, in which all the gadgets live and the library functions. So in this diagram so far, we've already pushed arguments onto the stack. That's what the args block represents. And so next, we're just going to push the return address and then any other stuff we need to facilitate restoring the return address onto the stack there. So that's going to point to the next instruction, of course, on the shellcode instructions. Then we'll just push the address of printf onto the stack. And then we are going to do what we said before. We're going to break the rule, or break the abstraction by pointing RSP to the shellcode stack. So now SP, this shellcode stack pointer, is equal to RSP. So this way, library functions will use the shellcode stack, not the shellcode instruction space as a stack. That would be detrimental. So now finally, we can just return into printf. Printf will execute. It'll return. And then it'll restore the shellcode return address. And then everything's as we want it. All the post conditions are met. But you may have noticed there were some parts that were pretty vague or hand-wavy. So this time I'll go in almost fully in depth. But don't worry if you get lost. So pretend we're back where we started. We're about to execute the library call. We've already pushed this time three arguments onto the stack. This is what we're passing to printf. The 3 arguments we're passing to printf. So first off, we might actually need to add some padding to the shellcode stack because some library functions expect 16-byte stack alignment. So we'll have to check that first, conditionally push some padding value onto the stack, and then we'll push the shellcode return address onto the stack. But then we'll use that pop RSP gadget I mentioned earlier, and this will help restore the shellcode return address. Then we'll push the address of printf onto the stack. And then, first let's notice that we've been pushing values onto the stack, and we've been modifying, by doing that, we've been modifying the shellcode stack pointer. But we don't want to do that, because once the, we don't want to leave it like that, because once the library call ends, we want the shellcode stack pointer to be exactly where it was as it started. So that should point to arg1 in this case. So what we can do to get around this is we just push the shellcode stack pointer onto the stack, the old one pointing to arg1, I should say. And then finally, we're ready to kick off execution of printf. And so this is my favorite part. And that is because to start execution of printf, ironically, we use a leave gadget. So we're executing a leave gadget to start calling a library function. And even more ironically, each library function ends in a leave instruction. So this is how it works. So leave is really 2 instructions tied into one. It's a move RBP into RSP, and then a pop. So the move just sets the target stack pointer to the shellcode stack pointer. And then the pop instruction restores the old shellcode stack pointer, which is pointing to arg1 at this point. But now we know that printf is going to preserve that RBP. So it's going to be still pointing to arg1 once printf exits. So we'll return into printf. It'll execute. It'll return. Then we'll execute this pop RSP gadget. And then just as planned, the gadget pops off the return address and puts it into the shellcode program counter, like that. And now the library call to printf is complete. Everything is back where we want it. OK, so that's how library calls work. It's pretty clear that they're pretty complex instructions. They take a lot of infrastructure to execute. And it turns out the libcall compiles to like hundreds of bytes of raw shellcode. So this is definitely actually a problem, because you probably can't inject all that onto a target program. You just might not have enough stack space that it's using. So the solution isn't immediately clear, but the solution I came up with was actually to split the exploit into 2 different stages. So the first stage is it's the exploit. It just does the bare minimum of behind-the-scenes setup to get the program initialized. So it'll initialize the shellcode stack, and then it'll map the rest of the shellcode into memory at a fixed address. And remember, the rest of this shellcode, they're not executable instructions. They're ultimately just gadgets. So we'll never actually be directly executing attacker code. And then so stage 2 that's the payload. So we map that into a fixed address. And that contains the main shellcode program. And there's no limit to the size of this. So I'm done presenting the internals of ROPC. Here are some ideas for future work. So I think one big improvement would be if it was position independent. So one way to do this would be to add some additional instructions to ROPC-IR. So adding relative jumps and relative calls. That way that you wouldn't need to map the stage 2 payload at a fixed address. That's not ideal. But I don't think this should be too difficult because all you would need to do this is do math on RSP or move it into a different register and do math on that register. Basically just additions or subtractions. And also, so I did just note that library calls can be very large, but it turns out there's almost all library calls use identical gadgets. So you can factor out all of these gadgets into another subroutine, or maybe a little less than a subroutine, but and then jump to that code so that if you have more than one shell library call, it wouldn't take up twice the size. It would just be a little bit more. So that would be one way to limit the size of the exploits as well. OK, so finally, we've gotten to the demos. So first, I'm going to show my Fibonacci sequence generator exploit. So let me pull up the virtual machine I've been working in. That's weird. Here it is. OK. That's big enough. OK. Yeah, didn't make it any bigger. OK. OK, so first, see if I can make this text a bit bigger. OK, we'll just go like this. OK, so first let's look at the vulnerable program I wrote. So it just contains a very stupid buffer of overflow vulnerability on the stack. It tries to read from standard input into a very small buffer of only 8 bytes. But it reads something up to 300 bytes, so very vulnerable. So let's just try running it on so giving it input that doesn't crash it. So small input works. If you give it very large input, it'll crash, unsurprisingly. So what I did is I wrote a program in ROPC-IR that can exploit this. So so payload start just marks, that's the entry point into the program. And so each of these are just ROPC-IR instructions. What it does, it's going to compute the first 30 bytes, or sorry, the first 30 terms of the Fibonacci sequence. And each time it'll just call fibrec. So that recursively computes the Fibonacci sequence. See here, it checks if it's a base case. If so, it just returns. Otherwise, it'll compute it on smaller values and add those together. So of course, a very inefficient way to compute it. But this is just to demonstrate that subroutine calls work, as well as library calls. It uses a library call to printf to print out the value. And finally, a system call to exit. So now that we've seen that, I'm just going to remake the exploit and explain how this works. So this is the compiler in action. Here's ROPC -N2. That just means 2 stages. There's a configuration file that contains the target-specific parameters. And so the rest of these are basically the implementations of ROPC-IR instructions. That's why I didn't type all this out. It's very long. And finally, there's the source file that I just showed you. And so that was compiled to fib.sc. So now let's try running it. So actually first, here's another command that I need to run. So this is disabling ASLR. So it just doesn't work with ASLR enabled, so let's just disable it. And then hopefully, if this works correctly, what will happen is Echo will it'll read in part of this shellcode program. It'll try to print it out. Then when it returns, hopefully we'll hijack execution and print out the Fibonacci sequence. So let's see if it works. It's trying to print it out now. And OK, so it looks like it works. So it successfully hijacked execution and printed out the Fibonacci sequence. So there are a couple other So here's another example exploit. This is very basic. This is just showing you can also use this compiler to exec a shell, basically. Of course, it's kind of overkill in this case. So this time I'm going to use a slightly different program. It's called Echo3. It's the same program. It just opens up a file and echoes the value. So essentially it's cat, but it's the same code as Echo, basically. So same vulnerability as well. So let's just try it on a valid input. So all that hello.txt says is hello, echoes it correctly. If we gave it a bigger file, it would crash. So now let's look at so here's the source code for this executing the shell. Or sorry, it's really what it does is it calls system, and you supply the it'll read on standard input. So file descriptor 0, what command should be executed. So what it does is it calls this function called read command. It allocates a buffer. It reads some value. It reads the string, the input string, and then it calls system on that and returns. So more simple than the previous one. Let's just make sure it's made. And let's try running it. OK, so first we can just try a simple command, ls. So that seems to work. You can drop a shell and do ls and do other things that you would do once you have a shell, like exit. OK, so that also works. So it's also able to do simpler things like other linear shellcode can also do. So if we take a step back for a moment and think about it, we're actually kind of back where we're started now. So we have, originally we had a target program so it has a target stack. It uses it to store return addresses, and basically it uses a call stack. It also stores local variables there. And if we think about it, the shellcode program we have now also has its own stack, and it uses it for storing return addresses and also local variables. So it turns out you can also have bugs in shellcode programs if you abuse buffers, if you have buffer overflows. So I actually wrote a third exploit. So this one's actually a meta exploit. So it exploits that previous exploit I showed. So it's not just a coincidence that it was called vulnerable.sc. It actually has a vulnerability in it. So this exploit's going to exploit that by providing extra long input, and it's going to print out the binomial coefficients using this recursive formula just to go along with the theme. So let's look at the source first. Nothing really new. This is a bit more complex just because the recursive formula was really hard to debug as I was writing it. Next, I think I'll write a debugger for ROPC-IR. OK. All right, so if everything goes properly, vulnerable SC will hijack execution of echo. It'll try to execute this strange series of bytes we're giving it. It'll overflow buffer on the stack. It'll try to return, but really it'll return into this shellcode, and then hopefully that will print the binomial coefficients. And so it does. So actually, so the way that I also, even though I did write binomial in ROPC-IR and compiled it with ROPC, it did require one modification, just of 8 bytes. And that's because it turns out there is not an equivalent for a non-executable stack for shellcodes, which have their own stack. So you can do the traditional kind of exploit where you just write directly executable instructions onto the shellcode stack and jump to those. So that's what this binomial shellcode does. Okay, so that concludes my talk. Before we start going in more circles and writing meta exploits. So I'd just like to say thanks to Travis Goodspeed. He provided very valuable feedback on preparing this talk. And so my LinkedIn is, and GitHub and email are up there, and this is the link to the project on GitHub. And so that's it. Thanks for coming. And does anyone have any questions?
First off, I want to say thanks because this is brilliant. But I want to ask about your use of EBP, or rather RBP, as the shadow stack pointer. I thought that in x86-64 there was an optional extension to the ABI to keep using RBP in the traditional way as the pointer to the beginning of your own stack frame, like as a debugging aid, but that if you weren't choosing that optional extension, that freed up RBP for use as another general purpose register. And so like GCC by default doesn't do any of the magic things that you want with RBP, doesn't save it, doesn't restore it, doesn't do any of those things, and instead would just clobber things. How did that affect the development of this, or am I just remembering the ABI wrong?
So I didn't know that was the case. When I was working in the virtual machine, all the library functions I ran into always started with push RBP and then ended with the leave instruction. So I guess if there was,
maybe it's an unpopular extension and people aren't using it because humans expect there to be a base pointer, even though there's enough relative addressing that you don't strictly need it anymore.
Yeah, well that's interesting though. I don't know how, that would definitely change things. I think at that point you might just have to hard code the stack pointer and just store it
in memory somewhere.
Yeah.
May I ask it? The other question was about the availability of gadgets that you want, like in particular a pop ESP. How hard is it to find a pop ESP? Because why does a normal program ever want to pop ESP?
Yeah, so I mean that's why I kind of like using that gadget because it's just so, it's kind of very
it's perfect.
Meta. Yeah, it is perfect.
But do real programs have pop ESPs
I think so.
available?
I think I found that instruction. It was an intend instruction because sometimes there are hidden instructions in gadgets, or sorry, in x86. If you look at offsets from intended instructions, but I think this one was, yeah, it could have been that. But yeah, you can find a surprising number of them. And also, I just want to note it's kind of harder on x86-64 because if you want all the gadgets to operate on 64-bit values, some of those instructions require a prefix. So that really narrows down the number of gadgets you can actually use.
So I had a question about code size generated. What sort of code size expansion based on your shellcode intermediate language size relativity are you seeing? Or is I guess that's based on the gadgets you found?
Yeah, so I am not exactly sure. I think it's in like around 8 kilobytes, I think. So it's pretty large. I think you could reduce that if you tried really hard. I was sort of assembling these by hand, but one of the things with ROPC-IR is you could automate the process since it's really just an instruction set architecture. But yeah, so it was large. So that was worrisome in the beginning. But splitting into 2 stages, I think, helped a lot. But still could be better.
And then I guess the other question is, let's say some of the instructions can't be fulfilled by your ROP gadget source, I guess. Is there a way where you can just say, oh, just disable these functions in my intermediate language because I can't fulfill them?
Well, I guess there's no like official way to do that in the compiler. I think a workaround would just be to not use those instructions and then just give it like a false or filler, implement it in a false way, just like implement it, make it an empty instruction. And that it would probably work fine. But
So if you can do all the subroutines and call stuff, what barriers are there still left to writing shellcode in a higher level C-like language and building larger frameworks for it? I don't know, I mean, uses may be limited, but are there barriers to something like that?
so I think the only barrier is so it's called ROPC-IR. It's like an intermediate representation, and that is what some compilers produce. So some C compilers produce intermediate representations. So that was kind of the idea, was to not. One of the advantages of having it lower level is it's easier to take existing compilers and just modify their backends or their code generation components to actually target this assembly language and not, say, x86. Yeah.
In the process of defining the instruction set you needed, were you sort of aiming for a Turing complete kind of state, or are you aiming more for like Turing good enough to just kind of get your tasks done and kind of limiting to what you really actually have as a goal from a shellcode point of view? Because obviously you don't have to do everything. You just need to do good enough, right?
Yeah, well, I think, so I was aiming for Turing complete, I think, from the beginning. And I mean, one of the reasons is I guess one of the things I thought of is it's very suspicious if you have some program that shouldn't be execing anything, it suddenly starts execing something. One way to get around it is if you have a Turing complete set of gadgets, then you never have to exec another program, and you can even exit normally. So it's a lot less suspicious, I guess. But I guess I didn't think about that in the beginning. I thought it would be interesting to see if you could have a usable Turing complete source language.
You mentioned it doesn't work with ASLR enabled. Is there a potential extension where if you have identified a information leak that could be fed into the compiler so then it would work with ASLR?
So I haven't thought about that much yet. I suppose if there could be, someone could write an extension that would make it work with it, but I haven't really looked much into it, so I can't say either way, I guess. Any other questions? Thank you.